Welcome everybody. We're going to be continuing in this video our discussion on random variables. In this video, we're going to focus on finding what is called the mean value or the expected value of a random variable. Alright, now what I mean by mean value or an expected value is if we were to carry out an experiment that gave us a random variable an infinite number of times, what is the value that we would expect most of the time whenever we run that experiment. Alright, it'll make a little more sense whenever we see an actual value, but let's take a look here. I've got three examples to go through, and in the first one what I want to do is show you how you calculate the expected value when each outcome for a random variable is equally likely. Alright, read along with me. Cards labeled with the first four perfect squares are placed in a box. Let V be the random variable representing the value of a card chosen at random from the box. Determine E of V. Alright, first, before I explain anything else to you, I need to explain to you a little bit of notation. We're trying to find expected or mean values here, and this notation is how you indicate that you're trying to find the expected value of a random variable. That means the expected value of V. Alright, now I already said that we're working with a situation here in which all the values are equally likely. So each of the outcomes here has a probability of 1/4. Now simply when all the outcomes are equally likely, the way you find the expected value or the mean value is you just find the mean of all of the possible different outcomes. Okay? So we have to be dealing with experiments in which our random variable is a number, right? For that to work, because if you're going to average things, you've got to have numbers to do that with. But we're simply going to say that the expected value of V is equal to 1 plus 4 plus 9 plus 16 divided by 4, and that's 30 over 4. Often you'll write expected values as mixed numbers if they come out to be fractional values, and so we would say this is 7 2/4 or 7 1/2. Alright, now what does that mean? Oh, you don't ever actually think you're going to get a 7 1/2 when the outcomes are 1, 4, 9, or 16, but you're going to get that higher than that 50% of the time, you're going to get lower than it 50% of the time, and just because you've got some larger values right there, the mean is a little bit closer to the top half of the data set than it is to the bottom half, if you will. Anyway, expected value. You don't ever get a 7 1/2, but we expect the average of all our outcomes to be a 7 1/2. Now let's see what happens whenever the outcomes don't have equally weighted probabilities. In a small promotional giveaway, a store invites, I don't know why I said a story, but a store invites customers to draw a gift card from a box containing 70 $10 cards, 25 $25 cards, and 5 $100 cards. And X is going to be the random variable representing the value of the card drawn. Alright, let me do a little editing there. We don't want that word story there, not that you care. You just care how the problem goes, but anyway, I'm going to make it right. There we go. I feel better already. Now, I've gone ahead in the probability distribution and written the probabilities of getting each value gift card, right? We had three outcomes, a $10, $25, and a $100 gift card, and 70 out of 100, or 7/10, were $10 gift cards. 25 of them, or 1/4, were $25 cards, and 1/20, 5 of them out of 100, were $100 gift cards. Now here's the way the expected value is going to work. Alright? If we're trying to find the expected value of X, here's the formula. What you do basically is you take each outcome and you multiply it by the probability that it will occur, and then you find the sum of those products for each outcome and its corresponding probability. Now the formula for that looks like this. You find the sum of each outcome X times the probability that the random variable equals that outcome. Alright? Now in this case then, that means we'd be multiplying 10 times 7/10, and we'd multiply every outcome by its probability, so 25 times 1/4, as well as 100 times 1/20th, and then we're going to add those together, and that'll give us our expected value. Now we can do some canceling in places to make the math a little bit easier. Those 10s will cancel there. Nothing cancels in the second product. The 100 can become a 5. The 20 become a 1. So we've got 7 plus 5, or 12, right? From here, that's 7, that's 5. We got 12 plus 25/4. And that's the same thing as 48/4. Plus 25/4, so 73/4. And if we write that as a mixed number, as I said, expected values often are written, then that's going to give us 18 1/4. Now, in the context of the problem then, that means if I'm a person that goes and draws a gift card from this box, I'm expecting on average that I would get $18.25 from that draw. That's what most of the customers would have gotten. Okay, so there you go. That's how you find the expected value when the outcomes are not equally weighted. Got one more problem that I want us to work on in this video here, and it's going to use that idea of expected values, but it's going to be a little bit of a twist on it, a little bit of a challenge, if you will. It says here that the random variable D has the probability distribution shown. All right, you see there's 4 outcomes, and they're not equally weighted. We know the probability of getting a 5, we know the probability of getting a 65, but the outcomes of the probabilities of getting 15 or 35, those are not known. Okay, those are represented by variables. And I'm telling us in the directions here that we're going to find the values of A and B given that the expected value of D is equal to 38. So here we know the expected value, and we're going to try to use that to find some of the probabilities that go along with certain outcomes. Now, here's how we're going to go about finding out A and B. Let's first just go ahead and relate the formula for expected value to what we've got on our table here. You know that the expected value is calculated by multiplying each outcome with its probability and then finding the sum of those products. Let me write that out. All right, you see I just did 5 times 1/6. Well, don't know why I got a 15 there then. 5 times 1/6 plus 15 times A, and so forth. All right, now 2 things I'm going to do here. I'm going to simplify the value on the right side a little bit. So we're going to have 5/6 plus 15A plus 35B plus, now if we do a little canceling over here, cancel the 65 and the 5, gives me a 13. Whoops. A 13 and a 1, so plus 26. And we're also going to go ahead and replace the expected value with what we know it to be, 38. Okay, now one thing I hope you notice here is that we have 2 unknowns, and we're not going to be able to find those unknowns using this equation alone. All right, we'll take care of that part in a moment. Hopefully you can already envision that we're going to have to use a system of equations to find the values of A and B, and we'll come up with that other equation. Let me go ahead and simplify this a little bit. Let's subtract the 26 from both sides and get 12 equals 5/6 plus 15A plus 35B. And then 12 is the same thing as 72/6. And if we subtract 5/6 from that, we're going to have 67/6 equals, all right, that 15A plus 35B. All right, now we need another equation if we're going to solve as we've already determined. And I'm going to come up here and let's think about where our next equation is going to come from. Well, that next equation is going to come from what we know about the sums of the probabilities within a probability distribution. We know they always add up to 1, don't we? So that means these values right here have to add up to 1. All right, that works out nicely for us. 1/6 plus A plus B plus 2/5 has to be equal to 1. All right, now 1/6 plus 2/5, trust me on this, is 17/30. And I will trust that you can figure out how I got that. And so we can say that A plus B is equal to 13/30. Now it'd be nice if we could substitute that A plus B directly down here. We can't quite do it as such, but what we can do is go ahead and get either A or B by itself, and I'll get A by itself. We can make that A equals 13/30 minus B. And then we can use the substitution method to be able to find out what it turns out B is equal to first of all. All right, so let's take this equation down here, and I'm going to substitute up here. All right, we're going to have 67/6 is equal to 15 times 13/30 minus B plus 35B. All right, I'm going to go ahead and use the distributive property there. 15 times 13/30, you can mentally cancel here, please. That 15 will become a 1, the 30 will become a 2, so you'd have 13/2. And I said mentally cancel because we still have to multiply the 15 times the B, right? So minus 15B plus 35B. All right, now that's going to be 39/6, right? Subtracted from 67/6. 67 minus 39 is 28. So we get 28/6 is equal to 20B. And then let's go ahead and multiply both sides by 1/20. So B would equal 28/6 times 1/20. Some more canceling. Don't you love all the fraction work that we got going on here? Pretty cool stuff. All right, we can divide that by 4 and get 7. We can divide this by 4 and get 5. And we have found then that B is equal to 7/30. All right, it took a little bit of work to get there, but we figured out what the value of B is, 7/30. Okay, and then now that we know the value of B, finding the value of A is not going to be that tough. 13/30, where I'm looking right here. 13/30 minus 7/30 is going to give you 6/30, right? Which is the same thing as 1/5. All right, now this is 5/30 plus 6/30 makes 11/30. 11/30 plus 7/30 makes 18/30 plus another 12/30. That adds up to 1. Very good. All right, we've got what we're looking for here. Let me just write the answers. All right, now you know that an expected value is the average of all the outcomes that you would get from continuously running an experiment with a random variable. And you've seen how to use that to, well, you see how to find the calculated or the mean value. And you've seen how to use the mean value or the expected value in order to find probabilities of certain outcomes within a probability distribution for a random variable. Thanks for your attention, guys. See you later.